So, starting the presentation. Yeah, thanks for the great intro. Today's topic is train and deliver machine learning models to production with a single command. It's a catchy topic, but let's take a look what's inside there. Yeah, thank you for coming. We're happy to welcome you on our webinar dedicated to leveraging Kubeflow for machine learning workflow automation. Let's take a look at the scope we will cover today. In the first section, we would like to align everybody on terminology and machine learning workflow best practices, just to get on the same page with here. In the second part, we will revise tools, in particular Kubeflow and Hydrosphere.io, that will help us to automate the steps from the first part. After that, we will make a deep dive into that topic and demonstrate internals of automation process. Yeah, in conclusion, we would be happy to take your questions. So, machine learning workflow. We'll start with a general machine learning workflow. On a high level, machine learning workflow includes the steps from research to maintenance: data preparation, model training, cataloging, deployment, integration testing, production inferencing, monitoring and maintenance are in between. There is still a place for variations depending on organization's structure and their machine learning maturity. So every company is different, we know. Let us quickly run through these stages to get on the same page about the before the deep dive in a later section. So, research. Machine learning project begins with research. Here we formalize tasks, requirements, criteria, define data sources, and the methods to be applied for the solution. Pretty obvious, quite obvious here. Data preparation should be very similar topic for every data scientist. A crucial requirement here we would like to highlight here is reusing data processing and transformation functions in the inference phase. So the data preparation pipeline has to be designed in a very modular way to be deployed in production later as part of the main machine learning model. Model training step also contains very well-known items like building, training, evaluating, and training the model. An interesting topic barely covered by the community is versioning of training data. It is very important to capture and version the data your model has been trained with in order to be able to get back to the same data set and train other models in the future. It will allow us to compare apples to apples when you track different models. Also, capturing a training data set metadata helps you to track the concept drift in production over time. Next, model cataloging is the term we would like to use for the following requirements here. So metadata extraction, including graph definition and weights, definition of inputs and output shapes, as well as the reference to the version of training data has to be indexed and saved to the immutable model repository alongside with the model binaries. That's after that, the model can be independently run on any infrastructure as a without any external dependencies, external hidden knowledge lost somewhere in between training and serving. So by model deployment, we mean launching the model microservice on a cluster and exposing API endpoints to the rest of the world. So other applications can send requests and get predictions. The most popular types of model API are HTTP, gRPC, batch, and streaming endpoints. Model integration step, model integration testing step is something that many companies do not even think about. It is required to check that deployed model works end-to-end. Usually it allows to catch configuration issues before the final production. Also, like replaying different data sets and asserting model metrics like accuracy or confusion metrics verifies that model works correctly on edge cases, manually created golden data sets, and others. Once the model has been trained, we can release it to production. Production operations is not a one-time action, it's a long-running process with many sub-processes and sub-workflows, but logically, for the sake of this presentation, let's consider it as the next step in a life cycle of machine learning model. Model performance monitoring is one of the sub-processes that contributes into reliability of production operations. System metrics monitoring, like latency, throughput, is essential for every microservice in production, just a general practice for any software that has been deployed. Model metrics tracking is required to continuously evaluate predictions using ground truth labeled captured in production, if possible, of course. And concept drift monitoring should profile input features and output predictions as well to find edge anomalous cases in production. And the last step here in the machine learning workflow is model maintenance. Finally, it comes to this step in the long term. At this step, we make alerts and perform troubleshooting when something happens to the model. Repairing and retraining the model requires new data sets to be sampled, as well as the way to gradually decay the old model. So, enough theory. Let's start reviewing a tool set. So in this presentation, in this webinar, we will cover a Kubeflow, the machine learning toolkit for Kubernetes, and Hydrosphere.io, the machine learning model management platform. What does it mean? What is a Kubeflow? Basically, Kubeflow began as Kubernetes template or blueprint for running TensorFlow. Over time, it evolved into a toolkit, loosely coupled tools and blueprints for machine learning on Kubernetes. The toolkit and loosely coupled are keywords here. TensorFlow, KTeep, and other tools are independently developed tools deployed on Kubernetes and orchestrated by Argo. Argo is also a tool in a Kubernetes ecosystem. Kubeflow pipelines is the latest addition to the ecosystem, a nice Python DSL on top of Argo YAML configurations, YAML configs. So in a nutshell, this is what Kubeflow is. So what's a Hydrosphere? Hydrosphere is a platform for machine learning models management. In the context of the Kubeflow toolset, this is an exact value add tool, a part of the toolkit. It's open source and it focuses on cataloging, deployment, inferencing, monitoring, and maintenance steps of the workflow that we've just covered. Let's take a look at the tools landscape in order to not to get lost. Too many tools today. This is a mapping between workflow steps and the tools from the Kubeflow ecosystem. Kubeflow is a very open toolkit. It doesn't enforce you to use one tool versus another. There are many tools for training, TensorFlow, PyTorch, you know it. There are some gaps in model cataloging covered by ModelDB and Hydrosphere.io. There are underserved steps like testing, monitoring, and maintenance where Hydrosphere.io could be used. And in this webinar, we do not force you to use something particular. We will provide a couple of options for each step, explain how they work under the hood, and let you decide what's the most appropriate for your organization. So switching to deep dive. Wonderful. So research, very quickly, skipping this, very familiar. For the sake of simplicity of this presentation, and in order to focus on just a workflow without spending time on like data science part, let's take the canonical example of MNIST dataset, MNIST problem. Data preparation, we'll start with downloading data. As I mentioned, yeah, we're gonna use a MNIST dataset to train our model. We'll use Python code for the rest of the slides. The code is pretty straightforward. We just download the MNIST archives and unpack them into desired directory. An important remark to make here is to explain where the data is going to be stored. To do that, we have to understand how the whole workflow is going to be executed. Each step we will be running in the separate pod. Pod is a term from Kubernetes world. I won't spend time on explaining it, assuming you know it. Which means that we store data. If we store data locally in the current step, it won't be accessible for the next pod. In order to retain the data during for the whole workflow, we will use a volume mount. Base dir variable here simply points where that volume is mounted, and it's configurable from the environment variable. As a volume source, you can use any desired volume type supported by Kubernetes, share it on S3 or any other data storage. Side note, for the code for this workflow is available in our GitHub repository, and we will provide the link at the end of the presentation. Next, since we want to execute all the steps of our workflow as a pipeline, we have to build containers, which will represent each step. This is pretty simple. We just have to create a Docker file with the presented content, build an image from it, and publish it to Docker registry. Model training, the same straightforward code you should be familiar with. We will use one of the pre-made estimators, DNN classifier. Not much to say here, just a simple fully connected neural network classifier with Adam optimizer and learning rate configurable from the outside. Yeah, we define training and evaluation specifications and run the training. The crucial step here is saving the model, exporting the model from the training pipeline. We save it into safe model format under desired directory. TensorFlow has a strong exporting mechanism and allows us to save both graph definition and weights learned during training. We should build an Docker image for this step too, similar to the previous one. So basically, every step should be followed by creating a Docker container and pushing it to the Docker registry. Then model cataloging, probably kind of new thing you haven't thought about. There are multiple ways of doing that. The first one is do it yourself. You basically instrument the training pipeline to extract the metadata. You have to store that metadata somewhere in a database, in a file, in a whatever you decide to use. Use zip model and metadata all together and store it on S3 or push to Artifactory or push to GitHub. So It's like a very, as usual, do-it-yourself is very flexible, the most flexible way. It's up to your best practices and up to your desire to maintain and to build it yourself. Yeah. So there are options like ModelDB in TensorFlow in Kubeflow ecosystem. It's also like independently developed tool, but could be used in this workflow. It's have nice Python DSL to sync model with database, to sync test data, basically send the test data to database, sync metrics, and it has very nice UI for visualizing all that stuff. So we've made in Hydrosphere.io, we also made a bit of model cataloging. It's not a fully functional model database, but it is like an essential part that is needed for later steps for deployment and serving. So we made some particular architectural considerations and provided a nice DSL for pushing the models to the cluster. Here how it works. So when you execute like HS upload, it's just a command line interface. The tool versions, extracts metadata, builds Docker model Docker image, stores Docker image in a registry. So it provides immutable storage and versioning for the data while capturing required metadata for later life workflow steps. And yeah, on top of this, there is nice UI. You can basically discover different models, different versions, and their metadata. Basically, discover your assets to be used in production or in other environments. The next step, model deployment. Again, do it yourself. But Kubeflow doesn't enforce you use one option versus another. Usually, you would like to implement a Flask server, look up for model, then Dockerize that code, provide some kubeconfig, expose different kind of APIs required by your clients, and it should work pretty well if you want to do it yourself. Also, there are niche tools that are being built for particular machine learning framework, or particularly in case of NVIDIA, it's being built for their GPU modules. TensorFlow serving, PyTorch serving, if you're like fully dedicated to one particular framework without any like scikit stuff, without manual models, you could like nicely use these tools. So with what we've built a more general purpose deployment tool, which exposes just one CLI command to get these things done. And under the hood, how it works. So we take the metadata, we take a model and a pre-cooked, pre-built runtime optimized runtime, and we launch that model alongside with the runtime on a cluster. And based on the metadata, we generate HTTP, gRPC, and Kafka API. So that could be used in a different scenarios in your like business logic or whatever you have there. Again, so it's pretty exact decision that has been made, and the implementation, if it conforms with your like architectural vision, if it conforms with your guidelines and across the company, that would work. If you have like if you have a different vision and different view, that's probably currently the do-it-yourself is like another option you could consider. Then integration testing. Again, Kubeflow doesn't provide any functionality for integration testing, any module, any tool for integration testing. It's probably a bit far from current maturity of the tooling we have in the open source ecosystem. And here, like in most of the organizations that we see, it's a do-it-yourself option, basically implementing a testing script that takes some the data lines, send these to the model, gets predictions and asserts results. For this purpose, you need to maintain and capture somehow by different maybe processes, different data pipelines, this golden data sets, the edge cases, or just capture recent traffic from production. So the code might look like this, and just a straightforward Python code, not with some asserts. In our roadmap in like Q2, probably we would like to provide also like very tailored implementation that will expose like test API for the workflow. Step 7, production inference. So basically, inference means like you send request and get prediction back with a certain API. So in this particular case, it's just an example how you can call a gRPC API exposed by, in this case, by Hydrosphere, but yeah, it doesn't matter. gRPC or HTTP API is kind of universal across different platforms, different deployment options. It either Flask or whatever you use. So TensorFlow serving with very open here. The crucial part here it begins when you need to do things like A/B testing, like canary deployment. It requires a significant knowledge about the Kubernetes internals, Istio, and whatever you like depend on your cluster. So happily we have Istio, but like it's a very like a separate topic, and we can spend like another webinar on digging into production inference scaling, routing, A/B testing scenarios, canary testing, because for machine learning models, the A/B testing is not the same as for regular microservices. The traffic could not be split between different versions of machine learning models. It should use kind of aggregator and verifier after the predictions has been produced. So skip it for now. So for production monitoring, we usually use different levels of monitoring. It's system monitoring when we monitor latency and throughput and memory and CPU. That's usual. For also we monitor, as I mentioned, we monitor model metrics specific for like a first level of monitoring should be done on model metrics like accuracy and like precision recall, confusion metrics, variant under the curve, whatever you use it. The idea is, okay, if you have ground truth labels, you should calculate this as you go along. If you don't have these labels, you would need to monitor some secondary metrics like data distributions, data statistics, and others. So, and even if you have the ground truth labels, there might be a challenge to get it in time, right in time. Sometimes it takes like a month to get them, especially in like fraud detection use cases. Then you just use that secondary metrics that may get you provide you an insight that something is wrong in production, or something may require your attention. Yeah. And model maintenance, basically when alert happens, so for example, accuracy drops, then we need to find an answer why it drops. In like most of the cases, it drops because data has changed. And as like the next step, once we see, okay, data is changed, we need to have an answer for what exactly has changed. And just to see those examples that cause like edge cases that cause that accuracy drop, or it might be not an edge case, it might be just a natural drift of data in production. So and also the sequence, now it begins a different, maybe a business workflow, how to deal with that. Sometimes like you don't have that accuracy as the first level metric. You just start with secondary metrics and then realize, okay, it seems my accuracy has to drop in the during this period. So that type of business workflow and resolutions might be very complex. We won't cover it today. And yeah, when you have this, when you detected an edge case, and you see that a particular request is treated as an anomaly, for example, you need to know why it's treated as anomaly. And this is an explainability of monitoring alerts. That's like another step forward that to provide maintenance capabilities for your machine learning workflow. So the second part is, okay, we define that steps. Some of them are defined. They are very logical and very isolated from each other and packaged into Docker container. And now we would like to use Kubeflow pipeline, DSL, to run an actual automation of those steps. Here I want to give the word to Ilnur.
Okay, hi everyone, and I will continue with deep workflow dive. So once all of the containers, all of the executables that Stepan described above were created, we can switch to defining a Kubeflow pipeline. Sorry, yeah, that should work. Kubeflow pipelines represent machine learning workflow as a set of Docker images that are responsible for one specific task, like downloading, model training, and so on. And we can connect those steps into a flow that will be executed as an experiment. To create a pipeline, we will use a Python DSL package provided by Kubeflow, which will translate the code that we defined here into a Kubernetes configuration files. Basically, pipeline is represented as a decorated function. And this function can be parameterized with the values that we would like to use during the workflow execution. Stepan said that some of the values during, for example, downloading the data were configured with the environment variables. So here we provide those environment variables. And when we create that pipeline function and export it and compile and upload into Kubeflow UI, those are the place where you can configure those parameters and just simply run experiments, as many as you want. So the first step is of course downloading, and we use a Monist pipeline download Docker image that was already created, but as we may remember that the downloading stage requires us to provide a mounting, a volume mounts. So here are just a few lines with code. You can add a volume to your containers. And the second stage, here we create a training operation container and additionally set a requirement for memory usage and core CPUs. Kubernetes cluster, you don't know exactly when your Kubernetes cluster have enough resources for your pipeline to be executed. So as the Kubeflow requires from the Kubernetes cluster to have an exact amount of resources that you requested to proceed the workflow. And as well, here we add some additional variables like volumes and environment variables. In the next step, we perform uploading such model. We create a we provide a volume mount where our model has been exported in a safe model format and upload it to the repository along with building a Docker image from that model and versioning it. As well as at this step, you can see that the function contains a file outputs keyword, which will map all the contents of the model version txt file to the model version variable. And we can use that variable in the next step of deploying an application. As you can see, here are the arguments keyword, and it has as an input an output from the previous container step. And here we additionally provide some environment variables pointing out where our hydrosphere cluster is available. The next step is testing. We create a testing image, a client that will basically just reach our model for the predictions, and it will as well count the accuracy of that model with the training data provided, and it will, well, not training data, test data, and it will assert that the level of accuracy is above acceptable level, which is provided at the bottom by acceptable accuracy environment variable. And the last step is just the cleaning. We clean up our environment, like deleting Monist files and deleting all intermediate TensorFlow files used during the training. And once that pipeline were created, we can compile it. At the end, we will use a Kubeflow compiler, and this will essentially just produce us with the pipeline tar archive, which inside contains a pipeline YAML definition of a Kubernetes resource. And to give the exact single comment that will run that pipeline is this. You can submit that pipeline that was generated by Kubeflow with the Argo CLI, and watch how it executes. Another step for you is to upload such pipeline into Kubeflow UI and see how everything works out. So that's pretty much it. The source code available for this webinar is placed here. And thank you for watching.
Thank you, Stepan and Elner. So speakers would be open to any questions. Feel free to put these questions in the chat box, and I'll be happy to forward these questions to the speakers. So there's a question by Anupam. Is it a cloud-based, or it can be in on-premise as well?
It can be used on premises. It's kind of like a cloud-based solution when you upload your model. You can as well deploy it on the premises using a Docker engine or something. Using Docker Compose to build every microservice that it uses internally to create it.
There's actually another question by Guang, and he's asking where the models are stored.
Hello. Okay, Stepan is unmuted. Let me follow up on the previous question. Kubernetes itself is could be run anywhere, on-prem, in the cloud, any cloud. So all the cloud providers has right now managed versions of Kubernetes. It means that the whole solution Kubeflow with Hydrosphere could be run anywhere. Could you repeat the second question, please? Where the models are stored.
Where the models are stored. Yeah.
So as I mentioned, there are a couple of options where the models could be stored. So Kubeflow itself, it doesn't provide you a model storage capabilities. You can store it by in S3. You can push it into Artifactory, whatever you would like to use. You just you have to manually manage those versions, folders, and so on and so on. What we built in Hydrosphere, we pushed the models into Docker registry. So our architecture principle is immutability. So and Docker registry is a very good immutable storage for any kind of executables and services. So we build a Docker image and push it there. So your models are being stored in Docker registry under a certain tag or whatever.
All right. So yeah, I'm giving the handle of Q&A to Stepan. So there's another question by Michelle. How do you reuse the data cleaning logic between training and inference? Do you extract it into a Python library, perhaps?
Okay, interesting question. Cleaning for inference, you don't need a cleaning logic because inference is happening all the time. It's a production environment. Physically, as I mentioned here, that production inference is not something that is being executed from the Kubeflow. You deploy the model and then it's being used by your users, by your clients. You don't need to clean up anything there. This is my answer.
All right. We have another question by Marvin. So she's thanking you for the talk. So in the case of MNISE, no pre-processing is needed, and I noticed TensorFlow transform from TensorFlow extended is still using Python 2.7. What is the best tool that you use for pre-processing?
For pre-processing, the best tool is Python. Just if you 1 second, I will. Where's my? Yeah, here I put just a Python as if you need to transform your data, you usually do that in Python. For MNIST data set, It depends. It depends on, it's a very simplified use case, but if you have certain images coming from the upstream, you probably need them to shrink it a little bit, to resize, and all those steps should be executed as part of the serving pipeline as well. That means that you would need to create just a function, Python functions that do that in both training side, and reuse it between training and serving side.
Got it. So Fisayo says that I'm very new in the machine learning space. Please, in the simplest way possible, what would you say Hydrosphere is, so that I can read up more on it and explain it to my team if we are to adopt it?
Yeah, actually, I wanted to highlight that before we started, that like webinar requires a knowledge, a familiarity, at least with like Kubernetes, because the terms we use, like pods and the others, are very hard to get, and when you're very new to this. Also, machine learning. I have a challenge explaining it to people who are very new in machine learning about Hydrosphere. It's probably for teams and companies who tried to do something, tried to build like a very first model in a laboratory, and not even a model, just have a general knowledge about what's going on, and tried to play with Jupyter notebooks and so on. So in a short, there is a new category that Gartner has been released recently as a machine learning model management, and basically it addresses this steps of machine learning lifecycle. And where in this space we simplify cataloging, deployment, integration, testing, monitoring, and maintenance of machine learning models. That's essentially who we are. But actually, the purpose of this webinar is more like of revealing the Kubeflow and its open architecture and open vision. From the one hand, it doesn't. It's not a platform. It doesn't provide you a turnkey solution, but it let you decide and let you choose as many options as you like, and choose like use a TensorFlow serving plus Hydrosphere plus something else. And probably the main conceptual point of this webinar in this nice, a very ecosystem which is in a very early stages of adding value into this workflow steps.
Got it. Yeah, we have another question by Nitin about Kubeflow, and they're asking, can we use it as a workflow through an MLDL algorithms in a distributed architecture?
Say again the second part of the question. Can we use it as a workflow?
Can we use it as a workflow through an MLDL algorithms in a distributed architecture?
Yeah, of course. So the fact that it is like cloud native, Kubernetes native, it is designed from the day one to handle this distributed architectures and distributed workflows. You probably know some. So workflows in general is not a new thing. We've been building workflows for like 1,500 years, Jenkins, Luigi, Airflow. Also, it's all about building workflows. Here, the difference of like Argo, that it is Kubernetes native workflow engine, and Kubeflow pipelines, currently what they do in a nutshell, they add a nice DSL, Python DSL, purposely built for machine learning workflow, which basically generates an Argo configuration files to be deployed and executed on Kubernetes. So the very long answer, but yeah, I'm just feeling that the audience didn't get some details what I have just mentioned. So I'm just reiterating this presentation based as an answer to the questions. Thank you for this.
Yeah. So yeah, we'll be taking like a few more questions since we are approaching the end line of the webinar. There's another question by Miles, and so Miles asking, when monitoring was mentioned, the speaker spoke of accuracy and alerting when accuracy was taking a dip and locking in to adjust and check. What methods are recommended in your opinion for tracking this production real-time accuracy? Namely, how do you know the model was inaccurate?
Okay, good question. So there's nothing new here. The same way as you calculate an accuracy of your model in a training phase, you basically take the actual label, take the predicted label, and calculate root mean square error there. The same way in production, when your model has predicted something, at the end of the day or at the end of some cycle iteration, you will get the actual predictions. The challenging question, the actual result. Yeah. The challenge is if it's hard to get, for example, a fraud detection. A real label that a particular transaction is fraudulent or not, that is usually like available in a month or even 3 months after a manual curation and manual review of people. In this case, you can if you don't have an actual label, you can't calculate that model metrics. There is nothing new here, and then you use, as I mentioned, that secondary metrics. So what may give you insight about the degrading of your model, like distribution of your input variable, input features, distribution of your predictions. Because predictions, the output of the model is not just one prediction. It might be, for example, in a self-driving car, it might be like bounding boxes, and how your model behaves here can provide you a very good insights that something goes wrong there. And yeah, the automation part of tracking an actual model accuracy in production is just having an ability to run it continuously against predictions and actual labels. Run it continuously in a batch mode or whatever. We internally would just write a function, assert function, and run it in a batch mode, like every day, every hour, whatever frequency is required for a particular model.
All right. So this would be our last question to our speakers. We'll be forwarding rest of the questions to speakers through our email and getting back to each of you individually. So our last question is by Anupam. So Anupam is asking, if we need to take a machine learning solution to some other location in a separate infrastructure, do we need to have Kubeflow on the other side?
Yeah, good question. So Kubeflow, not. You can like push the model to if that separate infrastructure has something that has an API. No, you don't need to have Kubeflow there. So it just orchestrates and just uses this API. But yeah, The question is, no, it's not. It doesn't constrain you in this case.
Got it. Yeah, so thank you, Stepan and Ilnur, for hosting this webinar, and thank you to all the attendees for joining it. Yeah, looking forward to seeing you in ODSC East if you wanted to attend the conference. Thank you.
Thank you, everybody. Thanks for the questions.